in today's video, we are going to be talking about the properties of water and how do we use these properties to help support life. So the first thing that we need to think about, why is water important for life? So we're going to talk about different characteristics of life and how they tie into the properties of water and how those properties of water can better help things to survive on the planet. So, basics of water. Water is dihydrogen monoxide, H2O. So we have two atoms of hydrogen paired with one atom of oxygen. And these atoms are going to be held together by covalent bonds. Covalent bonds, we talked in the last video, is a sharing of electrons. So we have hydrogen and oxygen. Both of those have their electrons. In this case, oxygen has 6, while hydrogen only has 1 in order to fill that octet. Oxygen needs 2 electrons. Hydrogen needs either no electrons or 2 electrons, but since they are both non-metals, they both share their electron pairs, which means that oxygen now goes up to 8 and hydrogen goes up to 2, which makes them both happy. Now, in this situation, oxygen being much bigger than the hydrogen wants the electrons much more than the hydrogen. And what this does is it creates a charge between the two of them. The oxygen having more access to the electrons makes it more negative, while hydrogen having less access makes it more positive. There's less of a negative charge there. The proton charge powers it out, which means that the hydrogens will be more positive. We consider this to be a polar covalent bond. Polar, if you think like the North and South Pole, or better yet with magnets. Magnets always have a positive and a negative end. Whenever you try to stick those positive sides together, they repel one another. Same thing with the negatives. So in this case, we have a polar covalent bond where we are sharing electrons unevenly and creating a partial charge between those two atoms. On the other hand, if we have no unequal sharing, we consider this to be non-polar covalent. Non-polar being that there is no positive or negative charge between these two, so they share them equally. Polar covalent, as you can see in the diagram here, we have one that is sharing unequally with the other, which means we have this partial charge shown by the Greek letter delta. And then if we have a complete exchange of electrons, then we get that ionic bond that we talked about in the last video. So if we look at this molecule of oxygen, you can again see because the oxygen is bigger, it's going to have a stronger pull on those electrons. And what that's going to do is it's going to lead again to that partial positive and the partial negative of the water molecule. So why is this important? Why do we need to know this? Well, water is able to form these bonds called hydrogen bonds that are kind of important for all of the properties we're going to talk about. So hydrogen bonds are not physical bonds, they are just mere attractions to those opposite charges. So in this case, opposites are going to attract, and positive is always going to seek towards negative. So the hydrogen in one atom being positive is going to be attracted to the negative charge in the oxygen of a different atom, and that is going to lead to this kind of bonding between the water molecules. So looking at this diagram, you can see we have our 3 water molecules. We're going to have opposites attract here, the positive to the negative of the oxygen. We're going to form these hydrogen bonds between these two atoms. Again, not physical bonds, so they can be separated fairly easily, but they still act as kind of a bond between these two molecules. So that leads us into the actual properties of water. So, like I said, all of these properties, or a lot of them anyway, are going to focus on that ability of water to be polar and to have hydrogen bonds. So the first properties we're going to talk about are adhesion and cohesion. So water not only likes to interact with itself, but likes to interact with the other substances around it. So adhesion is the ability of water to stick to other things. Typically, these have to be polar or ionic. They need some sort of a charge to form that kind of hydrogen bond connection with the other substances. You can see this if you've ever poured out a cup. Typically, what happens is if you don't pour it fast enough, the water runs off the side because the cup in this case is polar. It's going to have that kind of attraction to it that the water is just going to stick to and run off the side and make a mess. Cohesion, on the other hand, is the ability of water to stick to itself. So this is through the process of hydrogen bonding. And we usually see this if you've ever seen a drop of water or raindrop. They're held together by this cohesive force. So they stick together because the hydrogen bonds between them are going to keep them all in one contained area. So take a moment, look at this diagram of adhesion and cohesion. This is a comic depiction of adhesion and cohesion. Why is this comic wrong? Okay, so you should see the issue here is not between cohesion and adhesion itself. Cohesion, again, water sticking to water, that makes sense. Adhesion, water sticking to the sides of the container, that's also accurate. The issue is how these two are being bonded together. So you can see in this case we have oxygen bonding to oxygen. We can't have that. So if they were to make this more accurate, what they could do is they could put the hands holding on to the hydrogens rather than holding on to each other. That way we show this attraction from positive to negative, and we get a more accurate depiction of those hydrogen bonds. We also see this when we talk about plants. So plants, especially trees, they have to take water from the bottom of their roots all the way to the tip top of the tree. And they use both cohesion and adhesion to do this. So as water molecules move up, the sides of the container, or the stem in this case, are going to use adhesive forces to allow the water to stick to it, while cohesion is used to pull the water upwards. And we call this process capillary action. So this is when water kind of goes against gravity. It uses both cohesion and adhesion to stick to the sides of a container. So you can also see this if we measure liquids, especially graduated cylinders. You can see this in straws, you can see this in pipettes. The water will stick to the sides of the container as long as the container is polar or ionic. So when we go to measure things, we want to measure actually at the bottom of this meniscus, this little bubble here, because of these adhesive and cohesive forces. So capillary action is going to pull the water up. Again, we can see this in trees. The capillary action is going to allow the tree to get the water from its roots all the way up to its leaves. Now, if we just focus on cohesion, we can get forces like surface tension, or properties like surface tension. Surface tension is the thin kind of film on top of the water created by hydrogen bonds sticking water molecules together. So you can see in the diagram over here, we have all of these water molecules doing their thing, creating all these hydrogen bonds. But at the top, we have this layer of water molecules that are very strong. They're going to hold the surface of water together and keep them very stable. And what happens with this is different things can take advantage of this. For example, you may have seen a water strider. I've heard them called pond skimmers, water skimmers, Jesus bugs. There's a whole bunch of common names for them. But they are able to walk on the water rather than swim in it. And they do this because their legs have tiny hairs that you can see under a microscope. And these hairs allow for the water strider to maintain this surface tension. So you can see in this picture, they make kind of divots in the water. It doesn't break the surface of the water, but it has these little divots on the water. And these divots allow the water strider to glide on top of the water without falling in. which is a very good advantage for these guys because they are predators. So they usually take advantage of other insects that don't have this ability and fall onto a pond and get stuck. So these guys can hunt using the top of the water. So in this diagram, you can see again, all these water molecules are sticking together, and through those hydrogen bonds, we have connections that cause the surface to be very stable. Our next property is that water as a liquid is more dense than its solid counterpart. So typically, density we refer to as the amount of matter in a given area. Usually can be found using the formula density equals mass divided by volume. We're not going to actually do any calculations of this in this class, but for the sake of explanation, I'd like to at least give information about it. So density is the amount of particles in a given area. And as a liquid, it is more dense than ice. We can see this if we go to any of the polar regions. You can see the ice floating on top of the on top of the water. Same thing if you ever get a glass of water, typically the ice floats to the top. And this doesn't happen with a lot of substances. Most of them, they have solids that are much more dense than their liquid counterparts. And the reason for this is, again, those hydrogen bonds. So if we draw a molecule or a little collection of water here, each one is held together by those hydrogen bonds. And as the liquid freezes, as the water freezes, these atoms actually spread apart. So the hydrogen bonds force these molecules to spread out. And as they spread out, that means that their overall density is much more spread out. It's much lower. If something is less dense than the liquid it's in, it's going to float. So in this case, the ice is going to float on top of the water. And this is really important for a couple reasons. Number one, it keeps our polar ice caps actually floating on top of the water, so the sea level doesn't actually rise. But also for places that get very cold temperatures in the winter. So you can see in this picture, we have fish that are living in a pond while there is ice on top of the water. Typically, ice will form from the top down due to that low density. And so this means that things that live under the water are actually able to survive. If this were not the case, if we had it so that ice was more dense, what would happen is we would either have a freezing of the lake from the bottom up, or we would have a layer of ice that freezes, sinks, freezes, sinks, and gradually push the organisms back out of the water. So all life did, at least according to evolution, come from aquatic sources at one point. So without this property of ice being less dense than water, no life would have existed in the first place. The oceans would have, if the oceans froze, they would have killed all life in the ocean. Same thing, fish and things like that nowadays would not be able to survive due to the ice pushing everything out of the lake or out of the body of water and killing them. The next property we're going to talk about is the ability of water to be a universal solvent. So for life, a lot of the minerals and a lot of the compounds that we need are best able to be obtained through being dissolved in water. So in our bodies are about 70% water, which also means that all of the reactions in our bodies are taking place in aqueous environments. Aqueous just means that they are a watery environment. We consider these chemical reactions to be our metabolisms. You may have heard of the term metabolism before. Metabolism relates to all of the chemical reactions that are happening inside our body at any given time. And so what's important about water is that water can form solutions very easily. It is able to dissolve a lot of different things. In a solution, we have two parts. We have the solute and we have the solvent. So solute is the part that is getting dissolved. In this case, if we think salt water, the salt is a solute. The thing doing the dissolving is the solvent. And water is considered the universal solvent because of its ability to dissolve anything that has a charge. So anything that is considered polar and anything that is ionic, same thing we talked about with adhesion. Anything that has a charge is able to be dissolved in water, which means all of the minerals that we need, all of the ions that we need, all of the chemicals that we need to survive, most of them are going to be able to be dissolved in water, which makes them really easy for our cells to access and process. So the last property we're going to talk about is water's high specific heat capacity. So water is very resistant to changes in temperature. You can see this if you've ever gone to the lake in the middle of summer or the ocean in the middle of summer. You can see that even though it is very hot out, the water stays cool. You can also see it down in this diagram. We have the coast of California, Santa Barbara, LA, and San Diego all have temperatures in the 70 degrees, while the cities that are more inland have temperatures in the 100. San Bernardino and Palm Springs, both 100 degrees or above. So water can absorb a lot of energy without changing temperature. If you've ever tried to boil water, water boils at 212 degrees Fahrenheit or 100 degrees Celsius, which is very high. It takes a lot of energy to get water to boil. And that's due to the hydrogen bonds again. So the hydrogen bonds, in order to go from a liquid to a gas, you have to break the hydrogen bonds between the water molecules to get it to evaporate. So we have to put all of this energy into the water molecules in order to be able to get them to evaporate. And this helps us out a lot. So organisms, at least being made of water, use water to keep our bodies at constant temperature. We consider this to be part of our homeostasis, our constant internal environment. And water helps us to regulate that internal environment. It also helps us because we can do processes to help maintain that homeostasis. For example, sweating. So sweating is when your body releases water onto your skin to cool you down. What's happening there is, as the water is being released, it absorbs the heat from your skin. That absorption allows those hydrogen bonds to be broken to get the sweat to evaporate, and the sweat, as it evaporates, is going to take all of that heat with it. So overall, it's going to help cool you down because it's taking all of the heat on your skin with you. If you lose that ability to sweat, if you get something like heat stroke or heat exhaustion, typically heat stroke is associated with a loss of sweating, your body temperature will skyrocket, especially if you're in a very hot environment. Your body temperature will not be able to be controlled, and you can have a lot of health problems related to not being able to sweat. So with that, we are going to go through a couple review questions just to see, or there are a couple of review questions on this set of notes so that you can use to practice. We will be also doing an activity with the properties of water in class, but that is where this video will end. Next video, we'll talk about actual organic compounds. How do we get them? How do we combine them? And what are different classifications for organic compounds? So if you have any questions, feel free to email me, and I hope to see you in class.